Hello there, amazing students, amazing people, and all the lovers of chemistry out there. I'm so excited to be here with you on this good one today. My name is David, and all I do on this space is to take the mystery out of chemistry so Chemi can make history. All right, today we want to introduce the concept of organic chemistry, going through the basic things that you must know. So sit back, relax, fasten your seatbelt, and enjoy the show because it's going to be a roller coaster ride. All right, now let's start this video off by saying almost everything around you today is made up of organic compounds. From the air you breathe, breathing in, breathing out, to the food you eat every day, organic chemistry is literally everywhere. Now, here are some real life examples that you can relate to. The chemicals that make up your favorite perfumes and fragrances are made up of organic compounds. The food that you eat every day, the cooking process that makes up the meals that you enjoy, have something to do with organic chemistry, carbs, proteins, fats, and even spices. Now, if you say, okay, how about plastics and packaging? All we do is to package, gifts, hampers, and the rest. Organic chemistry has something to do with that. The phone case, if you're watching this on your mobile device, maybe a phone, or you're drinking, or you have a water bottle close to you, or even the clothes you're putting on as you listen to this, they have something to do with organic chemistry. Or maybe you just got back from the doctor's place not so long ago. The medicines and the healthcare facilities that watch out for your health have something to do with organic chemistry. And even the fuels and the energy you use at home on a daily basis all have something to do with organic chemistry. So basically, what I'm trying to say is organic chemistry touches every part of life. If you've ever enjoyed the scent of vanilla, for those of you who love ice cream, now that's an organic compound. The plastic in your water bottle, how about that? That's an organic compound. Even the medicine that cures a headache on a sunny day, that's an organic compound. So let's define this bad boy. Organic chemistry is a branch of chemistry, first of all. There are different branches of chemistry. There's food chemistry, there's physical chemistry, there's analytical chemistry. In fact, I could go on and on. But let's define it by saying organic chemistry is a branch of chemistry that focuses on the structure, the properties, and reactions of molecules that contain carbon. You see, when organic chemistry is being talked about, the first thing I want you to understand is that the element that takes the center stage is carbon. That's what we're focusing on. Carbon is unique because it forms strong bonds with itself and with other elements, allowing for the vast diversity of organic compounds. Now, here are some key concepts about organic compounds that I want you to take to mind. First of all, organic compounds involve carbon and hydrogen bonds. Now, all organic molecules, I beg your pardon, all organic molecules contain carbon, and many out of that all contains carbon that bonds with hydrogen. For example, your hydrocarbons, which are a very good example of organic compounds. On the other hand, many organic compounds also contain oxygen, nitrogen, sulfur, and phosphorus. A very good example are the proteins and the DNA in your body. Another thing about organic compounds that I want you to take note of is that they are found in nature and are also man-made. Organic compounds do not just occur naturally, they also occur artificially. In other words, they can be produced naturally or can be made by artificial processes. Okay, now they are also synthesized in laboratories. That's, for example, the plastics you use, dyes, and even medicines. They are produced by artificial processes. Now, even here is another point about organic compounds that I want you to take note of. Organic compounds are essential to life and industry. In life, for instance, the DNA and the proteins and the carbohydrates and fats contained in your food and in your body, they are all organic. And even in industrial processes, the fuels that are used, the medicines that are used to fight against diseases, food preservatives, clothing fibers, they are all based on organic chemistry. They are all based on organic chemistry. Now, let's talk a bit about carbon. First of all, carbon is the ultimate building block of life. It is unique among all elements because of its bonding ability. You see, carbon can form four strong covalent bonds that allows it to create a limitless variety of structure. This is why carbon-based molecules are found everywhere, from living organisms to fuels and plastics. Now, here is one fun fact about carbon that I want you to take note of. It is the only element that can form millions of different compounds, more than all other elements combined. Now, on the screen right now, there is a diagram of the structure of how carbon atom looks like. Now, here are some key concepts about carbon that I want you to take note of. If you check this out, you can see that there are four valence electrons in the structure of carbon. And by the way, valence electrons are the electrons that are contained in the outermost shell of an atom. Now, first things first, carbon can form four bonds. And that four bonds that it can form leads to it being able to give infinite structures. Carbon has four valence electrons, meaning it can bond with up to four other atoms at once. Now, that flexibility allows it to form single, double, and triple bonds with other elements like hydrogen, oxygen, and nitrogen. Now, when we get to the point where we talk about alkanes, alkenes, and alkynes, you'll be seeing why carbon is able to produce compounds like that. The next thing is that carbon can produce chain, ring, and complex molecules. Now, in the case where carbon produces a straight chain, by the way, what is a straight chain molecule? Straight chain molecule is a molecule that follows a linear buildup or a linear pattern in its structure. For instance, you can see at the top right corner of the screen, there is a straight chain molecule there that is being depicted. It is produced by a straight chain structure. Next is that carbon can make branch chains. It can produce ring structures and it can produce complex molecules. We're going to talk about all of these in detail. The next is that carbon is the backbone of DNA, proteins, and fuels. What is DNA, by the way? Now, let me explain DNA by using something that you can relate to. Before a building is built, there are many things to put in place. One of them is a building plan. A building plan tells you what that building is going to look like at the end of the entire process. How many rooms will be there, if it's going to be a duplex, a flat, a bungalow, stuff like that. Now, before a person is born or before an organism is formed, there is a blueprint, quote and unquote, a blueprint that shows how big or how tall, how fat or how slim that person is going to look like eventually. Now, that blueprint is what is called DNA. DNA is also called deoxyribonucleic acid, and it is the molecule that carries the genetic instructions for the development and functioning of an organism, essentially acting as the blueprint for life. Now, that DNA, which is the instruction or the blueprint for your life, it is built on a carbon based sugar backbone. And even the proteins that are contained in your muscles, your hair, enzymes, they are all made of carbon based amino acids. Can't you see how wonderful carbon is? Now, even coming down from there, into the concept of fuels, we have gasoline, coal, and natural gas, which are all hydrocarbons. They are compounds that are made up of carbon and hydrogen. So, carbon just has a whole lot of things that it affects in our daily living, which is why it is so, so important. So, now that you know why carbon is special, let's explore the history of organic chemistry. Now, organic chemistry did not just start today. There is a history behind organic chemistry. All right. Now, first things first. Centuries ago, scientists once believed that organic compounds could only come from living things. Now, that belief was what we called the vitalism theory. That vitalism theory was in place until in 1828 when chemist by the name Friedrich Holler made urea or produced urea in a laboratory. Now, that achievement proved that organic compounds could be synthesized or produced from non-living sources or non-natural sources. That was a big breakthrough in the year 1828, and that breakthrough shattered old beliefs and gave rise to modern organic chemistry, leading to life-saving medicines, synthetic materials, and even fuels. Now, here are some key concepts about the vitalism theory. First, Scientists always thought that organic compounds had a vital force that only living things could produce. For example, they believed that substances like sugar, proteins, and fats could only come from plants or animals. Now, this belief limited scientific progress because chemists didn't think organic compounds could be made in a lab until in 1828 when Friedrich Holler's discovery became the game changer. What was he doing? He was experimenting with some inorganic compounds, ammonium cyanide to be precise, when accidentally he created urea, a compound that is found in urine. You see, that is why I like science, because basically there are no accidents in science. Because what you call an accident is just simply a new discovery. Let me digress a bit. One of the great inventors in history by the name Thomas Edison, he was once reported to have tried to invent the light bulb, I think over 9,000 times, or I can't remember the exact number of times now, but he tried it in a number of ways that did not work. So when he was asked, and they said, "Sir, we heard that you tried a a high number of ways and it didn't work." And he said, "No, no, no, I didn't fail 999 times. I only found 999 ways in which it would not work." In the same way, science is just so amazing. Every mistake you think you make is just another way of doing something. All right, so this was a huge success because urea had always been considered to be an organic compound, meaning it could only come from living things. So the moment Friedrich Hohler did this, he proved that organic compounds could be made synthetically. No vital force was needed. So modern organic chemistry today has advanced because of that, and a world of possibilities has been brought to us because Holler's discovery led to the birth of synthetic organic chemistry. Now, because of that, today we can produce drugs, medicines, we can produce plastics and materials, we can produce fuels. If Holler never made this discovery, do you know how different our world would have been today? Our world would have been way, 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 way different from what it is today. Now, let's talk about some of the characteristics of organic compounds. What makes a compound organic? First, every organic compound contains carbon, which is the foundation of life. All right. Carbon's ability to form four bonds makes it available or ideal for creating complex molecules. For example, glucose, a simple sugar that fuels our body, is an organic compound. Now, most organic compounds have carbon to hydrogen bonds, right? A very good example is methane. You can see it at the top right corner of my screen. Methane is simply an organic compound that has one atom of carbon and four atoms of hydrogen, which gives it the molecular formula CH4. And by the way, methane is a natural gas that is used for cooking and heating. Next thing is that organic compounds are found both in living things and synthetic materials, right? A very good example is ethanol that is found both in alcoholic drinks and in biofuels. The next thing is that organic compounds have diverse structures. They have chain structures, they have ring structures, and they have polymer structures. Yes. So now, here are some major key terms and players in organic chemistry that I want you to take note of. Organic chemistry is a massive field, right? But to make it easier to understand, there are some key terms and players to get familiar with. Let's break them down. Hydrocarbons, the simplest organic compounds. Now, hydrocarbons from the name is simply a combination of two words: hydro, which stands for hydrogen, and carbon, which stands for the element carbon, of course. Now, hydrocarbons are molecules that are made up of only two elements, carbon and hydrogen. Now, what makes them special? They are the basis of fuels and industrial chemicals. Now, how many types of hydrocarbons do we have? There are three basic types, okay? We have the alkanes, which have the single bonds and are saturated. These are found in natural gases and gasoline. You can see on the screen at the top left corner, I have a structure of an alkane. I'll be teaching you later on in this YouTube channel how to name organic compounds. But then an alkane is simply a simple hydrocarbon that contains single bonds only throughout its structure. If you check out the structure for an alkane, you can see only single bonds present. Now, the next one, which is alkenes, means it is an hydrocarbon that has double bonds in its structure. You can see it at the middle structure there amongst the three that I have on my screen. The middle structure there shows that this hydrocarbon has double bonds in its structure, and alkenes are actually used for making plastics. And then the third one, which is alkynes. Alkynes are hydrocarbons that have triple bonds in their structure and they are unsaturated. They are found in welding gases. All right. Now, the next term that I need you to be familiar with, or you need to be familiar with in organic chemistry, is functional groups. Functional groups are also called the personality. I like to call them the personality of molecules, right? The term functional group refers to atoms or groups of atoms that give molecules special properties. Now, why are functional groups important? These groups determine how organic molecules react or behave and what they can be used for. Now, let me talk about this for a minute or two. Just like the way different molecules behave differently under different circumstances, that is how different people also behave under different circumstances. So that's why we have what we call the character or the behavior of people. There is something inside them that is making them to behave like that. In the same way, organic compounds have that something inside them that is making them to behave in a certain way. That something is called a functional group. It is that thing that a molecule carries which makes it to behave the way it behaves. For instance, now alcohols, or let me use the example ethanol for example. One characteristics of ethanol is that it would evaporate if you leave it in the open atmosphere. Now, the functional group of alcohol, OH, inside of it is what makes it to behave that way. I'll come there with more details. I just thought to clear that as we proceed. Now, for example, you have some examples of functional groups. First one is alcohols. Alcohols are found in your hand sanitizers and in some of the drinks that are made today. Another name of a functional group is called the ketones. All right, these are used in nail polish removers. The next one is called the carboxylic acids. This is found in vinegar and sour fruits. Now, all of these categories that I am mentioning, if you notice, each category has a way that each of them behave. For instance, in alcohols, they evaporate when you expose them to the atmosphere. Your hand sanitizer, you notice that every time if you want to preserve it, you have to cover the container so that it does not evaporate into the atmosphere. Now, for ketones, they are used in nail polish remover, and then carboxylic acids are found in vinegar and sour fruits. Now let's talk about biomolecules, which is the chemistry of life. Right? These are large organic molecules that make up living organisms. They matter because they are responsible for everything from energy storage to genetic information. Now, here are some key biomolecules. Carbohydrates. They store energy. For example, you have glucose and you have starch. Now, one thing about biomolecules you must know is that they are very large in terms of their sizes. Proteins, another example is proteins. Proteins take part in muscle building and enzyme formation. Now you have lipids, also known as your fats and your oils. They take part in cell membranes and energy storage. And then my favorite, nucleic acid, your DNA and RNA. These ones store genetic information, right? And they make up the blueprint of living organisms. Next is polymers. Polymers are actually the backbone of many of the modern materials that we have today. Now, what is a polymer? A polymer is a large molecule that is made by linking smaller molecules. I like to describe a polymer by using the word chain. Now, if you've seen a chain before, you would understand that a chain is made up by linking small units, right? Small repeated units. And when those small units come together, they make up an extremely long they make up an extremely long chain. Now that chain in chemistry, when small units come together, they make up what is called a polymer. Those small units are called monomers. So when they come together, they make up polymers. You'd agree with me that polymer was gotten from the word poly. Poly means plenty, and monomers, mono means one. So when plenty of one things come together, they make up a huge unit. They are used in clothing, they are used in packaging, they are used in electronics, and even medicine. Now we have different types of polymers. We have natural polymers, they are found in nature. For instance, silk, rubber, and cellulose, all these occur naturally. We have synthetic polymers, these are man-made. For instance, you have the plastic, nylon, and Teflon. And then we have a very good example of your synthetic polymer is your polyethylene. These are the plastic bags and bottles that are widely used. All right, now let's talk about some of the common organic compounds in everyday life. Organic chemistry is all around you. I said that at the beginning of this video, but why should you care? Organic compounds are not just in laboratories, they are in your food, they are in your medicines, fuels, and even clothes. Let's see some everyday examples. All right, now, organic compounds or organic molecules make up the nutrients that you eat in your food. They fuel our bodies, build tissues, and keep us healthy. Now, here are some key organic compounds in foods: carbohydrates, fats and oils, and even proteins. These are found in our food and they are made up of organic compounds. Now, in terms of medicine, pharmaceuticals, and life-saving chemistry, medicines are also made up of organic molecules that are designed to interact with the body. They help treat diseases, they relieve pain, and they fight infections. Now, here are some common organic medicines. Aspirin. Aspirin is a pain reliever and it contains a carboxylic acid group. And then we have antibiotics, penicillin. I'm sure many of you who may have sustained an injury, maybe an open wound before, one of the antibiotics that we use to rub on the surface of the wound so it does not get infected is penicillin. Now, penicillin is a very good antibiotic, and it's actually made up of organic compounds and it is used to fight bacterial infections. Now, talking about fuels that power our world, a very good example is methane, and it is made up of an organic compound. Organic compounds are the main source of energy in fuels. Fuels keep our cars running, they keep our homes warm, they keep our industries operating. Here are some key organic fuels: gasoline, these are used in cars, and even methane, which is a natural gas used for cooking and heating. Now, talking about plastics and materials, the chemistry of modern life. Many materials that we use daily are made of synthetic and organic compounds. Plastics are a very good example of them. They are lightweight, durable, and found everywhere. During the process of building a house, when most of the things are completed and then it is time to do the plumbing, pipes, rubber pipes are one of the things that they cannot do without. These are possible because organic chemistry has made the material available. Now, here are some common organic materials in the plastic and material industry. Nylon. Nylon is actually a synthetic fiber and it is used in clothes and in ropes. And then we have PVC. PVC is not your personal voter's card, by the way. It is polyvinyl chloride. This is used in pipes and credit cards. So if you have an ATM card with which you use to buy stuff, guess what? Organic chemistry made the provision of that ATM card a possibility. So say thank you, organic chemistry, for making my ATM card available. All right, now, so let's move on to what we have next. We're just summarizing what we've learned today. It's just an introduction into organic chemistry, okay? So here is the summary. Organic chemistry is simply the chemistry of compounds that contain carbon. It's all about carbon-based molecules, which are the building blocks of life. Carbon's special power. Carbon forms four bonds that gives it the ability to create diverse complex structures like DNA, proteins, and fuels. Organic chemistry is massively making impact in our world today. It's not just for scientists and laboratories. It is everywhere, from your food to medicines to fuels to plastics and cosmetics. Organic chemistry is at the heart of it all. Thank you for engaging with me in today's video. It was an introduction into the concept of organic chemistry. I'm so happy to bring this to you. In our next lesson, we're going to be learning much, much, much more. And remember, on this space, all I do is take the mystery out of chemistry so Chemi can make history. If there's any topic that is bugging you in school, maybe stoichiometry, there's a question you want me to deal with, please do well to post it in the comment section below, and I'll be happy to make a video concerning that and post it for you. Thank you very much for engaging with me on this. Till I see you in the next one.